Hi folks, we're going to take a look at page 175, number 10. So if we look at the problem here, some sort of train derailment that's causing pollutants to enter a pond, and they give us a whole bunch of information like how big the pond is, what the concentration is, and at what rate it's entering the pond. But really what's important is this function which models the concentration of the pollutant in the pond. Okay, and let's see what they're asking us to do. So they're asking us to sketch a graph showing the concentration of the pollutants after t minutes, and then what happens as t becomes very large. So this question B, you have to interpret what that means mathematically. So as t becomes very large, essentially this is asking for the end behavior of the function. So how are the y values or the c values behaving as the inputs, the t's, get very, very large. And then when a concentration level of 0.05 grams per liter in the pond is reached, the fish stock will be irreversibly damaged. They want us to know when this occurs. Okay, and this actually will lead us into what we're going into next class. All right, so let's get this function here, and let's answer the first one. So they ask us to sketch a graph. Okay, so let's start by sketching a graph here. Now this is already in simplified form, so let's take a look at what we need to sketch the graph. So we'll look for the x-intercept, okay, and that's going to happen at t equals 0. Let's look for the vertical asymptote. Okay, well, what's going to make this denominator equal to 0? It's going to be negative 200,000. So we have vertical asymptote at t equals negative 200,000. Now, right away, you should be thinking that I might use this to draw the graph. Having said that, I'm not going to consider these times here because I'm not interested in negative times. Okay, let's look at the end behavior. By the way, here I can see that the y-intercept will also be 0. Okay, if I input x equals 0, the whole thing is going to be 0. And the end behavior, well, this is a rational function with the same degree in numerator and denominator, so I just have to look at the quotient of the leading coefficient, so 30 over 1. So here we have a horizontal asymptote of y equals 30. Okay. And let's take a look at the sign of the graph. Okay, so the only places this can change sign is at negative 200,000 and at 0. In fact, I don't really care about this part here, but I'll just use this as an example to sketching these graphs. So really only care about what happens when it's greater than 0. Okay, now I anticipate that it's going to be positive. So when I put t equals 1 in here, I get 30 over 200,001, so it's going to be positive. Like I said, that's really all I need, but let me go on and find the other parts here. So let's say I take negative 1. 30 times negative 1 is negative, and then 200,000 minus 1, well, that's still be positive, so negative over positive, so this is going to be negative. And here if I say take negative 300,000, well, the numerator is clearly going to be negative, and 200,000 minus 300,000 is also going to be negative, so this is going to be positive. So if I wanted to draw this graph, okay, well, I'd have a vertical asymptote at negative 200,000. Okay, I have a horizontal asymptote at c equals 30. Okay, I guess here really I should have said c at t equals 30, but I used y, that's fine. And we have an x-intercept at 0. Okay, so in this region here, even though I'm not really considering it, I see that it's positive, so that means I've got the, on one side it must be approaching the vertical asymptote to positive infinity here, and then it'll go towards the horizontal asymptote of y equals 30. Okay, and then here we're going from negative to positive, so that must be going to negative infinity along that asymptote, and here it's going to be approaching our horizontal asymptote of y equals 30. Okay, so our graph looks something like that. Now you have to think, if you were trying to check this on Desmos, be careful because these numbers are very different, so you're going to want to change the scales on y and x, otherwise you're not going to get something that's going to look nearly like this function here. So remember, you can change the scales of y and x separately. Okay, so there we have our graph. But really, the only part of this that I'm interested in is the part greater than 0. Okay, so what seems to be happening is it looks like the concentration of pollutants is getting bigger, 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 bigger. Okay, doesn't look like it's actually going to cross this threshold of 30 grams per liter, but it's going to be approaching it as time goes on. Okay, now let's take a look here at what they're asking us in B. They're asking us what happens as T becomes very large. Okay, so we can say that as T approaches positive infinity, so as T gets very, very large, the concentration, okay, approaches the value of 30 grams per liter. Okay, now if you look at the question, it tells you that's the concentration of the pollutant. So I guess the idea here is that as this pollutant keeps going into the pond, eventually, if you just let it keep going, it's going to take on the concentration of the pollutant that's flowing in. Okay, kind of makes sense that it's never going to be above that. Okay, so there we go. We've answered part B, and now let's answer part C. So part C says when a concentration level of 0.05 grams per liter in the pond is reached, the fish stock will be irreversibly damaged. When will this occur? So that's actually a fairly small concentration, so they better get this pollutant out of that pond as soon as possible. So essentially what they're doing is they're giving us a particular concentration value. So they're telling us to figure out when the concentration value is going to be equal to 0.05. So if 0.05 equals 30T over 200,000 plus T. Okay, and what we have here is a rational equation. Okay, stands to reason that if we're studying rational functions, at some point we'll have to solve rational equations. So the question is how would we solve something like this? Well, you've solved equations where you have a variable in the denominator, and if you remember, the goal is to get that variable out of the denominator. So I'm going to do what I would do if I had, say 0.05 equals 2 over t. If I was solving one of these equations, what would I do? I would just multiply t to both sides of the equation to end up with a t in the numerator. Okay, and now I would solve the equation. Well, why not do the exact same thing? Let's take this expression of t, including t, and multiply it to both sides of the equation. So what we have here is 0.05 times 200,000. Well, that's too many. There we go. Plus t is equal to 30t. But look what we've done is by multiplying both sides of the equation by 200,000 plus t, I've turned this rational equation into a polynomial equation. In fact, a linear equation. Okay, so keep that in mind as to perhaps a method for solving these more complex rational equations that we'll be seeing. So here, let's do this. So I don't have my regular calculator, so I'm going to get to use this fancy calculator here. Okay, let's see if we can see that. So 0.05 times 200,000. Okay, so we have 10,000 plus 0.05 t equals 30t. So I'll bring the 0.05 t to the other side. So we've got, sorry, I think that was 10,000. Again, too many zeros. So we have 10,000 equals 30 minus 0.05. That'll be 29.95 t. And then t, I'll just divide this 10,000 by 29.95. Told you this is a cool calculator. And what do we have? We have 333.89. Okay, so now let's actually answer the question. Okay, if you take a look at the units here, time is given in minutes. Okay, so that means it takes approximately 333.89 minutes to reach a concentration of 0.05 grams per liter. Okay, so let's just do a recap. Step number 1 was to graph the function, and I just used the exact same procedures as I would to graph any other rational function. I find its its basic characteristics, and from there I'm able to graph the function. Even though I was only interested in that portion, when t is greater than 0, I took the opportunity to graph the whole thing. Okay, step 2 is they ask what happens as t gets very, very large. So in the end, we interpret that as just being the end behavior. And we see from the graph, or even from the equation, that as t gets large, the y values are going to approach 30. In this case here, grams per liter. And lastly, they want us to determine when the concentration was going to take on a particular value. So in this case here, I just used an old trick of eliminating the denominator, in this case here, that happened to have the variable. And from there I was able to solve. Okay, that's it for this one.